Hey there guys, in Unit 5, gotta cut that out. We're gonna try that again. 1, 2, 3. Hey there guys, in Unit 6 Notes B, we're gonna look at a specific type of equation called a net ionic equation. So what happens in a net ionic equation is that we of course have ionic compounds. These ionic compounds actually behave special when they are in water. By the way, there was a special term for that, where we put something in water. That would be our aqueous phase. So when we get to the part where we're looking at equations, that's how we can tell if something is in water. We're looking for that AQ phase. It's a really big deal. For an ionic, and has to be ionic compound, if we put that in water, it will go through a process called dissolution. So dissolution is really just a fancy name for dissolving. So basically what this says is you put an ionic compound in water, it breaks up, dissociates, it's going to dissolve in the water. The cation and anion will separate, will break up. If you remember, the ionic bond was the strongest type of bond and had some of our highest melting points. But water is kind of like its kryptonite. Water to an ionic compound is the same as kryptonite was for Superman. It's its weakness. Ionic compounds will break up in water. And by the way, molecular compounds will not. Only ionic compounds break up in water. So let's look at what happens in a net ionic equation. Net, as opposed to like gross, would show only what's important, only the things that change. So we are going to have to remove things that stay the same as you go from reactant to product. If there's no change, why even show it in the equation? So net ionic equations are going to kind of clean this up a little bit. They're going to remove what's called spectator ions. So what is a spectator in general? Just think like sports. Spectators are on the sides. They're not playing the sports, they're watching the sports. So the same thing with spectator ions. These ions are watching the other ions react. They're not the ones reacting. All right, so let's look at an example. Here I have lead nitrate reacting with sodium iodide to form a lead iodide. Notice here, the only solid, and then a sodium nitrate. So we have aqueous, aqueous, aqueous. So the first question is, which things will dissociate? The two conditions for dissociation, ionic compound and aqueous. Is this an ionic compound? Yes. Is it aqueous? Yes. So yes, it will dissolve. Sodium iodide, ionic? Yes. Aqueous? Yes. Yes, it will dissolve. Lead iodide, is it ionic? Yes. But is it aqueous? No. So it's not going to dissolve. Sodium nitrate, ionic and aqueous? Yes, it's going to dissolve. So 3 of the 4 things will go through dissolution. So what happens during dissolution? Let's just look at our first compound going through this process. So I'm going to start with my lead nitrate. And I'm going to break it down, kind of like decomposition reactions. So the lead will separate from the nitrate. But when this separation happens, then they form ions. They break from an ionic compound into their ions. What do ions need? What's missing here for me to call these ions? Charges. So if it's something from the periodic table, like if you know what column it's in, you should know the charge. But lead and tin and transition metals had varying charges, so that makes this one a little bit harder. Nitrate, on the other hand, is one of your things to know and love, and you should know the charge for nitrate is -1. So the charges are kind of set. And if I know this charge is -1, and I had 2 of them, and I know this was a neutral compound, I can kind of work backwards to figure out that that lead would need a +2 charge. +2 would cancel out with 2 minus charges. So the idea is you need to determine the ions first. You would need to do that for each of the compounds. For example, sodium and iodide would break up into my sodium and my iodine. But if I'm breaking this into ions, I need charges. So sodium, being in the first column, would have only a +1 charge, and then iodide, being a halogen, would have a -1 charge. Let's do this also for sodium nitrate while we're at it. This is going to break up into the sodium and the nitrate. So sodium, again, being in the first column, still has that +1 charge. And then nitrate, from our things to know and love, we know has a -1 charge. So you need to know what charges are typically formed for these different ions. If you have subscripts, that affects the count. So for example, here I had 2 nitrates. So would I then only produce 1 nitrate ion? Of course not, I would produce 2. So how can I show that without affecting what the ion is or what its charge is? The answer is those coefficients. So if I have a coefficient, I would apply that to both things that break up. And if I have a subscript, I would apply it only to that one particular atom or ion that's being broken. So let's start moving into our next step here. This is just showing how a dissociation works. So just for example, from our first one, our lead nitrate broke up into the lead 2+ and those 2 nitrate ions. Now, here's a question for you. Actually, let me go back to this part. Is this equation, the way it stands, balanced? Is this a balanced normal equation? Before we move into making it a net ionic equation, is it a valid equation to start with? See how I have 2 nitrates here and only 1 over there? And I have 2 iodines and only 1 here. So it's not balanced. So in order to balance it, I'm going to need coefficients. So first thing you want to do before you start the total breakdown is balance the equation. Once you have a balanced equation, now we can move on to the new part, writing a dissociation equation. So the dissociation equation is going to basically take the things that break up and write them as their ions. So let's start at the beginning. Our lead nitrate. So lead, we broke up to have a +2 charge, and the nitrate breaks up as a set of 2 nitrate ions. Because it was ionic and aqueous, we know it breaks up, and we are able to determine the charges and write them as separate ions. Now I'm going to move on to the next compound, this 2NaI. Ionic and aqueous, so I know it breaks up, and it's going to break up into those separate sodium and iodide ions. But the balanced equation has this coefficient in front of it. So that means I'm going to write 2 sodium ions and 2 iodide ions, showing that it breaks up into the Na+ and the I-, but because there was 2 molecules, I get double the ions each time. Now I'm at the arrow, so I'm going to go ahead and draw that. We still want to keep the reactants on the left and the products on the right. With PbI2, because it was a solid, it didn't break up. So I'm not going to write that as ions. I'm going to write that as the compound. And plus, now I have 2 sodium nitrates. So remember the sodium nitrate broke up into the sodium +1 and nitrate -1, but I'm going to have double each of those. So I'm going to have 2 Na+ and 2 NO3-. So the idea is you start with a balanced equation in the beginning, and then you go to a dissociation equation by identifying your charges, identifying things that don't break up, and by doubling when you have coefficients or subscripts. Notice how the coefficients end up as coefficients, and a subscript can also end up as a coefficient. The difference is, if it's a coefficient in the initial equation, it applies to both ions. Whereas if it's a subscript, for example, here outside the parentheses, it only applies to what's in the parentheses. So I only have 2 nitrates, but just the 1 lead atom or ion. So this is kind of the hard part here, writing the entire dissociation equation. It's big, and it's okay to leave off the phases at this point, but I'll mention this again at the end. We do want to include the phases when we get to that final answer for the net ionic equation. So here we've got our total dissociation. The next thing that I want to do is eliminate what's called the spectator ions. So I'm interested in what doesn't change. I need to find something that is exactly, I can't stress this enough, exactly the same on the reactant side and the product side. Same exact phase, same exact charge. For example, a hydrogen molecule would not cancel with a hydrogen ion. Two different things. I want to find two things that are exactly the same. So the lead here is an ion. Over there it's a compound. Not the same. Nitrate, 2NO3 minus, 2NO3 minus. Oh, we're not going to use red. That is exactly the same. And so that would be considered a spectator ion. Our goal here is to remove those things that don't change so we can focus on what does change. So now I've got my sodium ion, 2Na+. Let's check over here. Exactly the same. So I have another sodium ion as a spectator ion. Now I've got iodide ions versus it being part of a compound. Not the same. So I'm not going to cancel either of these ions or this compound. Notice how they actually changed. Over here they're ions, over there they're a compound. So now I want to write the equation as that final what changes, the net ionic equation. For your final answer, you need to bring the phases back. So yeah, we can be a little bit lazy here, but when you write that final answer, you want to include the phases. Ions are always going to be aqueous. And notice how where the lead came from, it is aqueous. Same thing with the iodide ion, came from this aqueous solution. And then the compound was solid. So I want to bring that back in the end as well. So let's start at the beginning. Pb plus 2, the ion, will be aqueous. And then I've got the 2I minus, again an ion, again aqueous. Now the arrow, and on the product side, I have the PbI2, which did not cancel because it was a solid in the beginning. So this is typically the type of answer you're going to get for a net ionic equation, where you have a couple of ions making a compound. Another version of this could be where you have like an ion and a molecule, and then there's a change in electrons, and so then on the other side you have a different ion and molecule, where they kind of trade places being ion versus molecule. We'll see some of those on the homework. So the idea here, finally got our answer, our net ionic equation, getting rid of the spectators. The dissociation equation doesn't necessarily have to include phases, but if you feel like you're going to lose track, feel free to go ahead and do so. Once you have it all broken down, you want to look for spectator ions. By the way, when I mentioned it had to be exactly the same, the coefficient should match as well, but I do see the mistake sometimes where students forget to balance the initial equation. So if you get to this point and everything's the same except for the coefficient, go back and see if maybe you missed balancing in the beginning. That should fix it so that they are exactly the same when you cancel here. So when you cancel those spectator ions out, we get that final total equation, or net equation, where the ions form the compound. You want to make sure at the very end, even though if you're lazy along the way, that you include your phases in the final answer. If everything was aqueous, everything would have canceled out. So the phases are actually really important. So we've got our aqueous ions forming our solid compound for our final net ionic equation. All right, guys, that's going to wrap up notes B from Unit 6. The next notes that you're looking for will be notes C for Unit 6, where we're going to look at the mole ratio as another version for doing conversions. So we'll see you there.